Dear students, welcome back to lectures on friction, and this time we will talk about its application. Now take the case of screws. So the screws are used for fastening and transmitting power or motion. The action of screw depends on the friction developed on the mating threads. For fastening, V threads are mostly used, but for transmitting power or motion, square threads are more efficient than other types of threads. So in this examples, we will study only about the uh, analysis of square threads. Now let us look at this particular figure 4a, where we see a square thread profile uh, screw, and this screw is moving through this nut body which is colored yellow, and as far the nomenclature is concerned, that this from this point to this point, that means between two consecutive threads, this distance we call as a pitch of the thread. Okay, and when we consider the motion of the thread, if we give a moment m given in this manner, then we get a linear motion of the screw upward. And of course, the screw is acted upon by some load W as shown in this particular figure. Now you can see this is the land of screw or the screw area, which is shown in this projected area. Okay, so here the screw area is this annular zone, which has got a outer radius of this much. RO we are calling as outer radius, that is written over here, and this is RI, the inner radius. Now for considering this particular situation, we will be always calculating based on this value Rm. That means the mean radius of the square thread will be always in our calculation. Now, there is also another idea normally we can have is that we are giving this moment m. Now, in the actual practice, how we create this moment m? We have seen that we are tightening the nut or the bolt head by using a wrench. Now wrench has got a handle. From the handle we apply a force P. Okay, so by applying a handle on the handle of force P, the wrench gives a momentum in this direction for this particular figure. Okay, so if we want to rotate this particular one by a wrench, then we should be having a wrench like this, and from the handle we get a speed and this. Now for our analysis, we will be considering as if this P is not given, we are giving a P which is merely nothing but M divided by this Rm. This is the P we are applying just onto this point, any point onto the screw face, that is, but here I have given this like this to create this moment. So same moment will be created anywhere you given P load, and that multiplied by Rm is equals to M. So this is an equivalent force that is applied onto the screw to give a moment to the screw. Another thing, this I forgot to tell you, that this particular one, this angle, you can see the inclination of this angle, and that is being defined by alpha, and this alpha is called the lead angle, and which is alpha, and that is given as an tan inverse L divided by 2 pi Rm. Now, what is L? L is called the lead of a screw. Now, what is the lead of a screw? The lead is the distance by which screw advances in one full turn. Okay, that means how much the screw, we give a full turn to the screw, how much it is moving. So normally we will say it will be moving about, if it will be moving equal to the pitch length only. No, it is not always. Okay, what happens? L is actually defined as N multiplied by P, where N is the number of starts in case of multiple threads. So you may be knowing this particular one about the multiple threads, but as an example, I can tell you that mm, if you're using a jam bottle, the jam head, the bottle head, you will be finding out few threads. It is not a continuous threads, and if you just count, then you will be finding out not only one thread is there. There may be one more than one threads in this particular periphery of the bottle neck. There will be one or two threads. Why this type of multi threads are used? For quick engaging or disengaging. Another example is that this is this in cases of unloading petrol from the petrol tanker, they are using, if you just carefully observe, then you will see that they're using just a nut to engage the pipeline with the tanker. So just by one or two rotations it gets attached. So there will be the multiple start threads. Okay, what happens that just by one rotation it moves much more compared to a single thread. So in many cases, multiple threads are used for quick engagement and disengagement. But surely what happens that these threads are not very good for a leak-proof type of joints. Okay, so for leak-proof type of joints, so always people will be using a single start thread or a fine thread. So these are the typical nomenclatures what is coming over here at this instant, and more we can find out in course of time. Okay. Now let us have a analysis of a screw from certain points of view in our actual uses. Now, if we consider, you have seen the threads in the earlier slide. Now you can imagine that we have stretched the thread for a certain portion of the thread we have stretched. Okay, so that I have written the representative portion of screw and knot thread. That is, the blue one is your screw thread and the yellow one is the knot thread. So what is happening due to the load W? The contact is taking place at the lower side of the screw thread and the upper face of the knot thread. Okay. So this representation we are giving for one full length. That means we have just stretched it. But this could be much longer. How much long? As much contact is there between the screw thread and the knot thread. Well, coming down to this particular idea of the analysis, which states that this load W and this is the reactive force R, this red color, the reactive force R, or the resistance force R. Why I am calling it as resistance force? Because basically it is a resultant of the friction force and the normal force. But one thing I would like to mention, that the figures are not drawn exactly to the scale to represent this vector. Okay, so it is a vector drawing. This R is the resultant of friction force and normal force. Although I have shown the nature of the friction force and the normal force, but for analysis I will be considering the R only. Okay, so so this is the R. However, the representation, what I have given just for the visual idea, for your visual idea, that how it actually occurs, how the the resultant force occurs. So I have shown as a resultant force, and somewhere I must have written that it might be also somewhere I might have written resistive force. Okay, so why resistive force? Because we know the friction is a resistive force. Okay, so that's the reason I'm using the R word sometimes also as a resistive force. Now, just I have given the idea, come back to the idea of what I was telling, that it is assumed that the total weight W is uniformly across the length of the screw, uniform distribution of this W, uniform distribution of the R is assumed over here. So if it is an uniform distribution, then it is obvious that there is no harm if I consider all the uniform distribution together as a total load, and as the representation I am putting at this particular point, and I'm considering this representative length for a one full rotation of a screw. So 2 pi rm is an one full rotation of the screw, and this I am writing lead, or the lead L. So what is this lead L? If it is a single stud screw, then L equals to P. So I could have written this also P, but as a general sense, I have written this as an L. Now look at the scenario that when you are winding the thread, that means trying to move the thread upward, then what we will be doing, you will be just like this particular blue strip, that is the thread strip, will move over the yellow strip for an upward motion. Okay, so if it is moving in the upward direction, then the friction force will be acting downward onto the bottom face of this screw thread profile. So if this is in, so R has to go like this. So R is like this. Then you can see the R makes an angle of phi with this normal reaction. So normal reaction will make an angle of alpha with the vertical line. Okay. So what is this phi angle? As you know, phi is nothing but tan inverse mu, means phi is the friction angle. So we call, as we have discussed earlier lecture, that is phi is the friction angle. So this is the friction angle. So in this particular case, if we can see that R has a component in the that it is in this particular direction, which is perpendicular to the axis, then the component of R perpendicular to the axis is nothing but R sine alpha plus phi. Or in other words, what is happening, that if I want to take the moment of this R about the screw axis, then I can write an expression for mr. This moment, mr stands for resistive moment because it is an R is a resistive force. So that will be Rm, this is multiplied by this length Rm, and R sine alpha plus phi, this total angle alpha plus phi, will give you a, resistive moment mr. And what is the direction of the resistive moment? That has been drawn over here. Okay, so what we require? We require an external moment mw for winding. Okay, mw represents that an external moment you are using as mw. So that means mw equals to mr. Obviously, this is the external moment should be overcoming the resistance onto the resisting moment due to this particular r. And the manner in which the mw has to be applied, the mw has to be applied in this manner. And if you are considering an equivalent p, then onto this onto the screw mean radius point, we have to give a P in this direction, or as if we are pushing by a P in this particular strip is then pushed by an horizontal force P. So this gives you the total uh, total moment value for about the screw axis. Okay, to to just to lift this particular screw. Now the sense of moment and P is as it is shown over here. Now we can also see that W is nothing but it is R cos alpha plus phi. So if we substitute the value of R as W by cos alpha plus phi in this moment M equation, in this equation, so we get a simple relationship mw equals to rm into w into tan of alpha plus phi. There is a sine phi divided by cos phi that brings out to be as tan phi. So this becomes a very simple equation that just to move the screw up, we require, this is the formula formula for finding out the moment required for winding the screw upward direction. That is Rm into W into tan of alpha plus phi. Now for downward motion of the screw, uh, this is particular the figure. Now once the screw is up in some position, then we want to again uh, move the screw downward direction. So if we want to move the screw in the downward direction, then what will happen? Let us see from this particular figure. The same figure I have drawn, but as because this particular strip is moving in the downward direction, so automatically friction force will be acting onto the upward direction. Okay. So if the friction force is in the upward direction, then what is happening, this particular r vector goes onto the left side of this particular vertical line. So this is the r vector. So what is the angle you can see, then angle between the normal and the r is as usual the friction angle. Okay, normal and this particular one is as usual the friction angle, and this is alpha. So here this particular angle becoming how much, it is phi minus alpha. So obviously again the component of this r in this particular perpendicular to this axial direction is in this way. So we can find out uh, the resistive moment is Rm into R multiplied by sine phi minus alpha. Therefore, moment required for unwinding the screw downward, we require a moment that is m un, means it stands for unwinding, is equals to mr. So what it means, the screw will unwind only if an external moment mu or a force p, this is then the force p is obviously on the other side, is acted upon. Otherwise the screw will remain in place. That means once you winded the screw, then it has gone to some position. Then for this particular scenario what we are analyzing, we require a moment of this particular sense or a p of this sense to bring to unwind the screw. Okay, so this particular phenomena that you require an external moment to bring it down, otherwise the screw won't come back, is called the self-locking of screw. That means the screw is self-locked. You have to open the lock by putting a moment in this direction. So what is the condition for self-locking? That your phi should be greater than alpha, as you can see. That means this particular angle of friction is more than alpha, So that's the reason this R has come to this side, and this side it has come. So therefore you are getting a resistive moment in this direction, and so that requires an moment of this nature to bring it down. So at the most, in the verge of slipping, phi should be equals to alpha. Here, what is the total expression of the moment in terms of load W? M, that means the M for unwinding is Rm into W into tan phi minus alpha. Now, let us look at the another situation. What is this particular situation? The alpha is greater than phi. Here we are considered phi is greater than alpha, then alpha is greater than phi. Look in this particular figure. I'm not considering F first. I am considering that that particular alpha is greater than phi. So what is the alpha? Alpha is the measure of the normal from the vertical, and phi is the measure of R from the normal. So this becomes your angle phi, and this becomes your angle alpha. So automatically you can see the R is on the right side of this vertical line. Therefore, what is happening? This R has got a component in this direction. That means and in this particular direction. Okay. So that means the friction force from the looking from the point of view of this R visual, you can see if the R is like this, then F should be also in this manner. That means what is happening, that naturally there is a tendency of this thread to fall down because this particular friction force is in the downward direction, but this particular one is creating what downward direction means what. That means it is moving upward. Certain amount of friction force is in the downward direction, is that means it is opposing the motion of the screw thread in the upward direction. But still, uh, R being in this direction, earlier case, in this particular scenario, R was on the other side of this end. Here, this side of the end, earlier the phi angle was other side of the end. Okay. So in the very first figure, if you recollect, then in that particular case, R is having moment. If you calculate the moment of this R about this, again about the screw axis, then this resisting moment is coming out to be Rm into R sine alpha plus phi. But what it is nature? Its nature is in this direction. That means what is happening, that to to resist this particular moment, you are requiring a moment in this direction uh, to prevent it from coming down. Look very carefully. This particular one is, this particular moment is this much. Means the screw is naturally getting unwinded. You do not have to do any job. It is naturally getting unwinded. As a matter of fact, you have to give an additional moment from the external or a load like that to prevent it from sliding down. So this condition is the worst condition. That means here you can say, hence to prevent unwinding, always an external moment M or P should act on the screw as shown. That means always you have to give a moment, otherwise the screw will automatically fall. Okay. So this situation is undesirable for any screw, because the screw after tightening, it won't stay in position, it will be automatically coming down. So these are the three scenarios of analyzing the screw. So from here we understand that uh, this, for unwinding, the condition should be phi minus alpha, and for winding the condition should be phi plus alpha, as we have seen in the figure 4b. So figure 4b and 4c are the right scenario for a screw, but not figure 4d. So this is the analysis of a screw, and what should be the screw design one has to keep this in mind. Now, after the analysis of the screw, we just, as usual, we take up a problem. This problem is a braking device. The braking mechanism consists of two pinned arms and a square threaded screw with left and right hand threads. Now what is happening? Say this is an right hand thread and this is an left hand thread. So uh, I will just simply tell what is the right hand thread and left hand thread. So I'm just giving a motion in this particular direction. So for this one, the screw will be rising, and as because it is the same axis, this this particular screw will be again dragged back. Means this one will be, this one is a, sorry, this one is the screw. I'm sorry. The knot will move in this direction, but as because this is left hand, this knot will be moving in this direction. So by one rotation, or by rotation in a single direction, this both these arms of this brake are, one is moving in this direction, other is moving in this direction. So this is very good arrangements normally made for the braking devices, manual braking devices. Just by you rotate a screw, and you can understand these are this brownish color are two brake shoes, and this drum is rotating at a this particular moment, having a particular moment, and it requires to say more. What is that? Let us see. If pitch of the screw is 4 mm, mean diameter 12 mm, and mu is 0.35, determine the tension in the screw when a torque of 3 Newton meter is applied to the screw. If the coefficient of friction between the brake pads A and B and the circular shaft is 0.5, this is okay. This is some circular shaft wants to stop it. Okay. What is the maximum torque aim that the shaft can resist? There are two parts. One, you have to find out the tension in the board. Now look, that is a calculation part. Look from our mechanics point of view. So if you are going on tightening, what is happening? This is dragging this side, and this is also dragging this side. So what ultimately will happen to this particular screw? The screw is in compression? No, screw is not in compression. Screw is in tension, because you can understand that if you are gradually tightening, it has got a tendency to move this way, but that you are doing by the screw, so automatically the load will be very higher on this side, and this is coming on this side, so automatically the load onto this particular screw body will be going in this side. Okay, means one side you are increasing the load in this direction, another side you are increasing the load in this direction by tightening. So obviously, if I draw the free body diagram, one shows the tensions in the screw. So that means that both the portions of the screw will be having tension T. Okay, this T is, I'm sorry, it is just looking as a part of the drawing. No, this is T, this is T. And there is some external moment. Uh, Look, actually, if I want to draw the free body diagram of the screw, this blue color is the only free body diagram. Okay. Uh, and this do not come into the free body diagram, because what is happening, you are giving the moment at the initial stage. Once the tension builds up, you are no more this 3 Newton meter is getting applied. So automatically the screw is in tension under the two forces, one in this direction, another is in this direction. So that I have just given. The figure shows the tension in the screw, and the moment shown is responsible to create tensions, but it is not applied after loading the screw. After loading the screw, it is not applied. So truly it is not coming in the free body, but I have just written it as a free body just to demonstrate you how the tensions acting onto the screw. Now let us come down to the free body diagram. I'm opening from this particular hinge joint. This is an flexible, this is an hinge joint attached, and this side is a screw. So this is a movable one. So as because there is a T tension onto this side, this bolt will get this particular will be dragged upon. So automatically it is getting a tension on this side. So this is the tension onto the knot portion. Okay, and this is the tension. This is the tension onto the knot portion. This is the tension onto the screw portion. Okay, and and the moment equation in this particular case for the screw thread is m multiplied by w into rm tan alpha plus phi, that we have learned for. Here w is replaced by 2t, because you understand the one loading part is for this what you call for this particular portion, another loading part is for this particular portion. So both are the same tension acting onto this particular screw, and so therefore I've written this is 2t into rm tan alpha plus phi. Now you know alpha is tan inverse pitch. It is assumed to be a single stud screw because nothing is specified. So 2 pi into rm, so that is tan inverse 4 by 12 pi, which is basically 6.06 degree. Similarly, phi is an friction angle, and which is 19.3 degree. Hence, we can see. So it's a, you can see that this particular screw is self-locking type. Why? Phi is more than alpha. Okay, if phi is more than alpha, then the screws are self-locking. That means once you apply this load and you bring it to some point, then it will be remaining like this. Then what you can see, this phi equals to tan inverse mu 19.3. Here m equals to 3 Newton meter. Hence torque is T is calculated from this equation. M I know. In free body 2, what we see, we consider impending condition to get the maximum friction force which each brake shoe can hold, because we wanted to know what is the maximum torque m the shaft can resist. Okay, as m is the maximum moment, so we are considering this impending condition which gives you the maximum force. So this is the free body diagram of this one. This is rotating like this. This is, so therefore the friction force is here like this, here is like this, and O, there is some reactive force obviously should be there because it is rotating on some bearings and others. So this is the figure. Now here we have two equations, ax equals to bx like this, and considering the moment about m, we can find out. So here you can see if I take moment about this point, I can find out ax in terms of t, because mu into ax, that is the that is the frictional force which is coming in line. Okay, so from here we can calculate the moment which can maximum it can be transmitted, because this is the maximum uh, friction force that this uh, particular body can, and offer. And by virtue of ax and bx equals to same and mu becoming same, this both are creating a torque opposing uh, this moment. So the maximum moment which can be created is 211 Newton meter. Okay, so this is the end of our lectures on friction. So I again request all of you to, although there are only 3 problems, just read the problems in your own way to understand these 2 applications, what I have told in this particular lectures.